Okay, so let me have your attention. You see, we are now more or less comfortable with thinking of the point at infinity, of functions behaving at infinity, analyticity at infinity, singularities at infinity. Okay, so we wanted to do that because we needed to look at functions on the extended plane. Okay, and this viewpoint is very important because it is not normally when you do complex analysis, say for example in a first course, you are worried about only functions on the plane, okay, on the complex plane. You are not worried about the point at infinity, okay, and but if you include the point at infinity, you get more information. That is the point. So I explained this last time, but let me again repeat it. So I am saying for example, look at let us take an entire function. Okay, let us take an entire function, take a non-constant entire function. Okay, then if you look at the little Picard theorem, what it will tell you is that the image of the whole plane is going to be either the whole plane or the whole plane minus one point, which is one value which it may not take, and that is the best possible. I mean it cannot miss two values. What it means is that if an entire function misses more than one value, it has to be a constant. Okay, so you see, and of course you have but then if I ask you now take this entire function and take the exterior of a circle of sufficiently large radius, okay, and take its image, what will the image look like? Okay, then you don't have an answer. You don't have an answer. So whereas for example, if you knew that if you can think of infinity as a singular point, and in fact if infinity is an essential singular point, okay, then you can apply the great Picard theorem, which will tell you that the image of every deleted neighbourhood of infinity will be either the full plane or the plane minus a point. Okay, so you can use that, which is a more powerful theorem, to say that if you have an entire function and suppose it's not algebraic, namely that infinity it's a transcendental entire function, that is infinity is a essential singularity, then if you take the exterior of a circle of sufficiently large radius, for that matter if you take exterior of any circle, okay, because exterior of any circle is going to be a deleted neighbourhood of the point at infinity in the extended plane, and if you apply the big Picard theorem, you get the information that the image of the exterior of any circle is always going to be the whole plane or the whole plane minus a point. Okay, and it will also give you the additional information that all the values it takes on infinitely many times. okay. So you see the advantage of thinking of the point at infinity, okay, you get more information. So so along these lines, you know that, for example, you can characterize entire functions as transcendental or algebraic based on whether infinity is an essential singularity or not. If infinity is not an essential singularity, then it is a pole or a removable singularity. If infinity is a removable singularity, then by Liouville's theorem the function has to be constant. If infinity is a pole, then the function has to be a polynomial, and otherwise it is a transcendental entire function. Infinity is an essential singularity, okay. Now what we need to do is, see, the whole aim of all this is we are trying to prove the big Picard theorem, and as a corollary deduce the little Picard theorem, okay. And theory required for that is to do analysis on compact spaces of meromorphic functions, okay. So you have to study the topology, and you have to do some analysis using compact families of meromorphic functions. So we need to worry about meromorphic functions. So let me start by telling you what a meromorphic function is. I have told this before, but let us go into that a little bit more detail, because that is something that gives you a link to algebra, okay. So the reason why a lot of complex geometry is connected to algebra is because of the fact that all the meromorphic functions, they form a field naturally, and that field is an extension field of the complex numbers, because the complex numbers always can be thought of as constant functions. Every complex number corresponds to the constant function given by that number. So and constant functions are of course meromorphic, okay, they are analytic. So you see that the field of meromorphic functions as a field extension of the complex field is the properties of this field extension in algebra, for example in Galois theory and things like that determine a lot about the geometry of the domain on which you are studying the meromorphic functions, okay. And this is extensively used, for example, in classifying Riemann surfaces, and more generally if you want to classify manifolds and so on, complex manifolds, you can use this theory, okay. It gives you an interface between complex analysis and topology and algebraic geometry, complex geometry, okay, and algebra in that sense, okay. Okay, so what is a meromorphic function? The definition is pretty simple. It is a function which is analytic on a domain, okay, but the only singularities it has are poles, okay. That is the definition of a meromorphic function. So let me write that down. So the field of meromorphic functions so here is the definition. Let D in the extended complex plane be a domain, okay. So I am looking at a domain in the extended complex plane. By mind you, it means that it is an open connected set, and of course we always assume that it is non-empty, okay. A meromorphic function on D is either an analytic function on D, or a function that is analytic on D except for poles, okay. So a meromorphic function by definition is a function that could be defined on D or D minus points, where those points will be of course isolated, they will be of course singularities, okay, and the point is that they have to be isolated, in fact they have to be poles, okay. This is the definition, okay. So we say that we often use the abbreviation, we use this short phrase analytic except for poles. That is what meromorphic means, okay. And Now we need to make a few observations. The first thing is that you see the number of poles, okay, the set of poles of the function, it may be of course empty, in which case the function is actually analytic or holomorphic, but if it is not analytic then it has poles, at least one pole, and the fact is that set of poles in D will be a countable set. So the first thing is that you cannot have an uncountable set of poles. So a meromorphic function will have only countably many poles, and what is the reason for that? The reason for that is because of second countability. Okay, see the complex plane is just R2, and you know Euclidean spaces Rn, they are all second countable because they have a countable basis. So you can take all the open balls centered at points with rational coordinates and with radii given by rational numbers, okay, and use the fact that the rational numbers form a countable set, okay, and then you get this collection of open balls centered at rational points with rational coordinates and having rational radii as a countable collection of open sets, and they will form a basis for the topology, okay, in the sense that any open set is a union of such sets, okay, and the intersection of any two sets like that of this type again is a union of sets of that form, okay. So it is a basis for the topology. So the topology has a countable basis, this is second countability, and now in particular, for example, the plane R2 or the complex plane as topologically is second countable. So you know what you can do is, suppose you have and of course any subspace of a second countable space is also second countable, because all you have to do is that you have to take the countable base for the bigger space and intersect it with the subspace to get a countable base for the subspace, okay. So so if you take the domain, you take any domain in the complex plane or extended complex plane, it will be second countable, okay. And by the way, if you are looking at the extended complex plane, of course it is homeomorphic to the the Riemann sphere, and the Riemann sphere is a subset of R3 real 3-dimensional space, and since real 3-dimensional space is second countable, the Riemann sphere being a subset is also second countable, okay. So the extended plane is also second countable, okay. After all, you are just adding one more point at infinity, and if you want, you can take all the disks centered at infinity, but of course you should not say finite radius, okay, unless you are looking at the images in the Riemann sphere with the point at infinity corresponding to the north pole, okay. But in any case, if you are taking a domain in the extended plane, it is going to be second countable, and now if you take a function which has poles in that domain, then the set of poles, the poles by definition are isolated, poles are by definition isolated singularities. So you have an isolated subset of a second countable set of a second countable space. An isolated subset will always be countable, okay. The reason is because since the points of the subset are isolated, you can cover each of those points by a member of the countable basis, okay, and you can choose different members from the countable basis because the points are separated from each other because they are isolated, and in this way you get a mapping, an injective mapping from the set of isolated points, in this case these are the poles, to the countable base, okay. And the moment you get an injective map, what it tells you is that whenever you get a map from a set to an injective map from a set to another set which is countable, then your original set is also countable because a subset of a countable set is countable, okay. Therefore you see the first observation is that a meromorphic function will have only countably many poles, and then if you are looking at a meromorphic function on the whole Riemann sphere, okay, which means you are taking the domain in the extended complex plane. Often I keep saying Riemann sphere because I think of the extended complex plane as a Riemann sphere, they are one and the same. So if your domain is the whole extended complex plane and you are looking at a meromorphic function on the whole extended complex plane, you get more. What you get is not only is a set of poles countable, it is actually finite, because an isolated set of points in a compact set second countable set is going to be only finite, okay, because you know one property of compactness is that if you had an infinite subset it should have an accumulation point, okay. Therefore the moral of the story is that if you are looking at a meromorphic function on the whole extended plane, then it should have only finitely many poles, okay. So let me write that down. So here are remarks. So remarks number 1, the set of poles in D is countable by second countability okay. So I am just saying that I am just using the fact that the poles are of course isolated and I am using second countability, okay. And the second remark is that if D is the whole extended complex plane, then the set of poles is finite. And that is because of compactness of the extended plane, okay. And then there is yet another fact. If you see the set of poles they form, of course they are a set of isolated points because poles are by definition isolated, but on the whole some of them might converge. See, they may be isolated points but they may get closer and closer and closer, okay. So like the sequence of real numbers 1 by n, okay, the sequence of real numbers 1 by n consists of, you know, it is a set of isolated points but it converges to 0, okay. So you could have a set of poles, okay, you could have a convergent sequence of poles, and then the fact is that this convergent sequence of poles has to converge only on the boundary, it cannot converge in the interior. The reason is that if it converged in the interior you are going to get a point which has to be in the domain of f, so it has to be either a singularity or it has to be a point of non-singularity, but then you know it cannot be a point of non-singularity, it cannot be a point of analyticity because it is approached very as close as you want by poles, and if a point is a non-singular point there should be a disk around that point where there are no singularities, but since this limit is being approached by poles, this cannot be a non-singular point, it cannot be a holomorphic point or analytic point, it has to be therefore necessarily a singular point, but then you assume that the singular points are all going to be poles, and here you have gotten a non-isolated singular point, that is a contradiction. Therefore if the set of poles of the meromorphic function has a convergent subset, then it will converge only on the boundary, okay. And of course this cannot happen if in the case when the domain is the whole extended plane, because when the domain is the whole extended plane, okay, the boundary is empty, alright, and there are only finitely many points, okay. So so let me write this down. If the set of poles has a convergent sequence of distinct points, then it has a limiting point in the boundary of T, okay. That point cannot converge inside T, okay. So you know so the moral of the story is the following. The moral of the story is when you are looking at meromorphic functions, and you are, of course, if you are looking at meromorphic functions on the whole extended plane, then there isn't anything. We are going to see that these are exactly the rational functions. Okay, we are going to prove that rational functions which are given by quotients of polynomials, they are exactly the same as the meromorphic functions on the extended plane. There is nothing more. Okay, but if your domain is not the extended plane, okay, then the meromorphic functions, if you look at for example, if you are looking at meromorphic functions on the unit disk, okay, then it is possible that you may have a sequence of poles that is converging, and it will converge to a point on the boundary of the unit disk, okay, and behavior at that point of this meromorphic function or this family of meromorphic functions is very important topologically, okay. So this is very important, that you need to study the boundary points also, okay, especially when you have sequence of poles tending to the boundary, okay. And of course what the remark says is that if there is a sequence of poles which is converging, it has to go only to the boundary, it cannot converge to your interior point, okay. Well, now so let me go ahead with this fact that I told you, that rational functions are meromorphic and the converse holds. A rational function is given by a quotient of polynomials f of z is equal to p of z by q of z, okay. So now I want to tell you something. I'm now all this time I was using the variable w, I was writing f of w g. The reason why I was using the variable w is because I wanted to study the point w equal to infinity, and the way I would do that is by studying g of z equal to f of 1 by z, which is f of w, by making the transformation w equal to 1 by z, okay. But now we have by now we understand how to deal with the point at infinity, so I am switching back to the variable z, okay. So z will be our complex variable from now on. So rational function is just a quotient of polynomials. So p q polynomials in z with coefficients in complex numbers. Of course quotient of polynomials of course includes even constants, okay. You can take q to be 1, okay. Constants are also treated as polynomials of degree 0, okay. In fact, in particular 0 is also considered as a polynomial, constant polynomial, and therefore you must understand that constants are also meromorphic functions, okay. And of course a function, a rational function like this is certainly a meromorphic function on the extended plane. That is very clear, because if you take a function of this form, if you take a function which is a quotient of polynomials, okay, it's going to, where is it going to have problems with analyticity? It's going to have problems with analyticity where the denominator vanishes. So you take those points, and where the denominator vanishes is just the set of zeros of a polynomial, that's only finitely many points, okay. And maybe some of these, maybe the numerator polynomial also has zeros at some of these points, so some of these zeros may cancel out, okay. But then the fact is that this function cannot have poles at points more than the set of zeros of the denominator polynomial, okay, and at all other points it is analytic. So it is an analytic function defined on the whole extended plane, with having only finitely many points which are going to be poles. So it satisfies the definition of a meromorphic function. So you see, therefore a rational function is certainly a meromorphic function, okay. And the theorem is that the converse is also true, okay. And so that is what I am going to talk about. the rational function is analytic on C union infinity except possibly at the zeros of the denominator polynomial, hence it is meromorphic on the extended plane. So the theorem is that the converse holds. The converse holds. So here is the, so essentially here is a theorem. If f of z is meromorphic on the extended plane, then f of z is a rational function. Okay. So there is no difference between meromorphic functions and quotients of polynomials. Okay, there is absolutely no difference, and you know, now this you should now think of it like this. If you look at the polynomials in one variable, in say in the variable z with complex coefficients, that gives you the polynomial ring in one variable over the complex numbers C square bracket z, okay, and you know that is an integral domain if you have studied that in algebra, and then this integral domain has what is known as a field of fractions, a quotient field. This is just like you get the rational numbers as a field of fractions when you look at the integral domain consisting of the integers. Okay. So if you look at the field of fractions of the polynomial ring in one variable over complex numbers, you are going to get just quotients of polynomials, okay, and these are precisely the meromorphic functions on the extended plane. So the moral of the story is that if you look at the extended plane, okay, the set of meromorphic functions automatically is a field. It is none other than the field of fractions of the polynomial ring in one variable over C, okay. So you can see that. So let's try to prove that theorem. Let me use another color. So proof. So you see, so I am given a function f set. The function is supposed to be considered on the extended plane, okay, which means you have to also consider the point at infinity, okay, and then the only information that is given to you is that the function is meromorphic, which means you know that it has only poles, and since the set in consideration is the extended plane, which is compact, you know I have already told you there are going to be only finitely many poles, okay, and it is possible that infinity may be a pole or not, okay. So first let's first deal with infinity first, okay, and so you look at the Laurent expansion of the function at infinity, alright, and you know that the Laurent expansion of the function at infinity will consist of both positive and negative powers of z, okay, and of course a constant term, and you know the singular part at infinity is the part that consists of positive powers of z, okay, and you know so now you see infinity, there are three choices for infinity. See, infinity can be either a removable singularity, okay, or it could be a pole, okay, and of course it cannot be an essential singularity because we have assumed the function is meromorphic, so it cannot have any singularities other than poles, okay. Now if infinity is a removable singularity, okay, it means that the if you take the Laurent expansion at infinity, okay, the principal part which consists of positive powers of z, or there is a singular part, has no terms, okay, and if you assume so it consists of only the constant part and the negative powers of z, okay. That is if you assume infinity is a removable singularity. If you assume infinity is a pole, which is the only other possibility, then you know that the principal part or the singular part consisting of positive powers of z has to be finite, so it has to be a polynomial of positive degree, okay, without a constant term, and of course the degree will be the order of the pole at infinity, okay. So in any case you are going to get the singular part as either 0 or a polynomial, that is what I am trying to say, at infinity. And if you take the function and remove that singular part, whatever is left is going to be analytic at infinity. That is what you must understand. So you see, this is something that we will use repeatedly. What is the point about the Laurent expansion at a point of a function? The Laurent expansion consists of a singular part or principal part and an analytic part, and if you take the function and subtract the singular part, what you will get is only a Taylor series, which will be actually the Taylor series of the analytic function, which is given by the difference of the function and its singular part. The moment you take away the singular part, the principal part, the function becomes analytic, okay. So this is a trick that you always use. If you want to extract the analytic part, what do? You take the function and subtract the singular part or the principal part, okay. So let me write that down. So let us first deal with the point at infinity, the point z equal to infinity. If the Laurent expansion of f of z at infinity is f of z is equal to sigma n equal to minus infinity to infinity a n u z power n, that is sigma, so let me write it like this, sigma n equal to 0 to minus infinity a n z power n plus sigma n equal to 1 to infinity a n z power n of z is this, and now let me call this fellow as p infinity of z, okay. This p infinity of z is what? This is the singular or principal part at infinity, okay. So this is the singular or principal part at z equal to infinity, okay. And of course whatever is left out here, this is the analytic part, okay. So you see, of course you should take this Laurent expansion to be valid for mod z greater than r for r sufficiently large. So it's so valid for mod z greater than r sufficiently large. So this is very important, okay. And so if you take, so the point is that, so if you take f of z minus p infinity of z, okay, this is going to be, this is analytic at infinity, okay, this is going to be analytic at infinity, okay, because f of z minus p infinity of z will only consist of the constant term a naught and negative powers of terms involving negative powers of z, and negative powers of z behave well at infinity, okay. And of course I should tell you something, if you look at the point at infinity, since we have assumed that f is meromorphic, this p infinity of z is not actually a power series, it is only a polynomial, okay. P infinity of z will be 0 if infinity is a removable singularity, that is a point of analyticity for f, and it will be a polynomial of positive degree equal to the order of the pole of f at infinity, if infinity is a pole. Okay, so let me write that down. Note that p infinity of z is 0 if infinity is a removable singularity of f and is a polynomial of positive degree equal to the order of f, the order of the pole of f at infinity. There is no other possibility. You do not have the situation when infinity is an essential singular point, okay, because we have assumed f is meromorphic. The only singularities that are allowed are poles, okay, fine. So now what you do is you look at, now let's look at the other singular points. See, I have assumed f is meromorphic, so it has only finitely many poles because it is meromorphic on the extended plane, which is compact. That is very important. Okay, there are only finitely many poles in the usual complex plane. Now I forget the point at infinity because I have already dealt with it. I now want to keep track of the points on the plane where f has poles. There are only finitely many. Let me call those points z1 through, let us say, zn. Okay, so let us write that down. Let z1, z2 and so on, zn be the poles of f of z in the complex plane. Okay, and again let me stress, this is very important, that you are getting only finitely many poles because you have assumed that f is meromorphic on the extended plane. The compactness of the extended plane is doing a big job here, otherwise you need not get finitely many poles. Okay, so you take these poles. Now whatever you did at infinity you do at each of those poles. Okay, so take any of those poles, then in a deleted neighborhood of those each of those poles, f admits a Laurent expansion, and if you take the Laurent expansion, if you take the singular part, it is going to have only finitely many terms. Okay, and of course the highest negative power occurring will be equal to the order of the pole. Okay, so let the Laurent expansion of f of z around zk be f of z is equal to sigma plus m equal to minus infinity, and I will call the coefficients as a, m, k. Okay, a, m, k, and mind you it will be z minus zk to the power of m. Okay, this will be the Laurent expansion. This is a Laurent expansion centered at zk, okay, and valid in a deleted neighborhood of zk, and of course that will be actually a disk centered at zk, and radius will be equal to the distance from zk to the nearest of the other zj's. Okay, so valid in 0 less than mod z minus. Okay, there of course rk, I am not writing it, rk is the distance of zk to the nearest of the other zj's, j not equal to k. Okay, and what is the principal part at zk? It is going to have only finitely many terms. Okay, and the highest negative power of z minus zk you are going to get, that is going to be the order of the pole of f at zk. So the principal part of f at zk is therefore pzk of f, which is going to be let me write as pzk of z, and that is going to be sigma, it is going to be m equal to minus 1 to minus let me put tk amk into z minus zk to the power of m, okay. Mind you, where tk is equal to the order of the pole zk, okay, of f. Mind you, these are all the powers of z minus zk are in the denominator. I am starting with m equal to minus 1 and going all the way up to minus tk, and of course the a minus tk comma k is not 0, a minus sub tk comma k is not 0. I mean, this is the coefficient of the highest negative power of z minus zk, right. So this is the principal part at zk, and now what you do is that you do the same trick as before. You use the fact that if you take the function and take away the principal part, whatever you are going to be left with is going to be analytic, because it is going to be a power series. So it is going to represent an analytic function whose Taylor expansion at zk is exactly that power series, which is the analytic part of the Laurent expansion. See, the you must always remember this, the analytic part of the Laurent expansion is actually the Taylor series of what analytic function? It is the Taylor series of the analytic function which is given by the original function minus the principal part, okay. So let me write that down, we need to use it, f of z minus p zk of z is analytic at zk, okay. So you see, so now look at the scenario. The scenario is, I have this meromorphic function f, there are these poles, finitely many poles z1 through zn, okay, and at each of these poles there is a principal part, okay, and if you take the principal part away, what you get is something that is analytic at that point, and of course there is also a principal part at infinity, okay. Now what I do is, I take the function and remove all the principal parts, okay. You take the function, subtract the principal part at z1, subtract the principal part at z2, and so on, you subtract the principal part at infinity, you subtract all the principal parts, and what are you going to get? You are going to get an entire function on the whole Riemann sphere, and what is it going to be? It is going to be a constant because of Liouville's theorem. An entire function which is if you are going to get an analytic function on the extended plane, which means you are getting an entire function which is analytic at infinity, and an entire function analytic at infinity by Liouville has to be a constant, it is a bounded entire function. Analytic at infinity means bounded at infinity means it is a bounded entire function and it is constant. So the moral of the story is, you take this meromorphic function and subtract all the principal parts, you are going to get a constant, and now you push all the principal parts to the other side, you will get that the meromorphic function is a constant plus all these principal parts, but each of these principal parts are rational functions, and a constant is also a rational function. So you have expressed the meromorphic function as a sum of finitely many rational functions, therefore it is rational, and that proves the theorem, okay. So that is all. So let me write that down. Now consider g of z is equal to f of z minus sigma k equal to 1 to n p z k of z. So these are the principal parts at those n poles, and then also take away p infinity of z, okay. Now what you get is g of z is analytic on the whole extended plane, and by Liouville therefore it is a constant. G is analytic on C union infinity, hence a constant by Liouville. So f of z is equal to constant plus sigma k equal to 1 to n pzk of z minus plus p infinity of z, which is meromorphic. On the extended plane, and that is the proof of that theorem, that a function which is meromorphic on the extended plane is just in fact what I want to say is not, of course it is meromorphic, the point is it is rational, it is rational. Okay, that is the point. We wanted to show that a meromorphic function on the extended plane is a rational function. Okay, so what you have got is you have proved that a meromorphic function f is a constant plus these principal parts, finitely many principal parts. So this part p infinity of z is a polynomial. Okay, it could be 0, and these are all involving negative powers of z minus zk's, finitely many for each k. Okay, and this is of course a rational function. If you take LCM, you will see that you will get a quotient of polynomials, therefore it is a rational function. And the beauty of this proof is that this proof also tells you that you get, for every meromorphic function you get a partial fractions decomposition. Each p zk, they are all the various terms of the partial fractions decomposition. So this proof in one stroke tells you that a meromorphic function has a partial fractions decomposition and is actually a rational function. Okay, that is the advantage of this proof. Okay, so I will stop with that.